Hey guys, so I've got another video here for you all, and my main focus with this one is to really hone in on this idea of a graded potential. So, a graded potential is defined as being something that's short-lived and creates a localized change in the membrane potential. In this case, the magnitude can vary. You can have a weak graded potential, you can have a really strong graded potential, and we're going to see that the current dissipates quickly. Okay, so we can see decay with graded potentials, and that's a concept that I'm going to circle back around to in another video. In addition, in this video, and I'm going to switch to a whiteboard here, I want to hone in on this idea of excitatory and inhibitory events, and I want to tie the excitatory events to depolarizations, the inhibitory to hyperpolarizations. And lastly, I want to talk about how it is that these excitatory or inhibitory effects are additive in nature. So these are terms that we've seen before: temporal summation and spatial summation. So let me turn to the whiteboard now. So we've got a neuromuscular junction here. So an action potential, right, comes down our neuron. And since it's a neuromuscular junction, we know that this particular neurotransmitter hanging out in these vesicles is going to be acetylcholine. So action potential comes down. You've got those voltage-gated calcium channels that allow calcium to come in, just like we saw, right, just exactly as we saw before. That allows for acetylcholine to enter this synapse. And then in this post-synaptic terminal, remember this is post-synaptic, and this area here is going to be the presynaptic terminal, right? So post-synaptically, when the acetylcholine binds to these specific ligand-gated channels, these channels open and sodium comes in through these channels. And conversely, you're going to have potassium that was previously hanging out in the higher concentration within these muscle cells that is going to leave. And so there's a bigger influx of sodium relative to potassium. And so I had described the ability to put a probe across this membrane and to actually measure the potential here. And so in the case of a skeletal muscle cell, we would actually see this at rest hanging out at about negative 90 millivolts. And so as that positive charge would come in, I always like to take a look at what would happen with our voltmeter. So if we would start out at around negative 90, and on the x-axis, you would have time, typically measured in milliseconds, right? So as the sodium begins to flood in, we go from this resting negative 90, and you start to get a positive charge along the muscle cell membrane, right? And if you recall, we had actually called that an end plate potential, or an EPP. So this increase in charge here is an end plate potential. Now, what I'm going to do is layer in a new term. So this end plate potential is a type of graded potential. In addition, and in this particular case, because we are taking the membrane of this muscle cell and bringing it closer to this dotted line, which is going to represent threshold, because it is getting closer to threshold, because it is getting more positive, zero would be way up here, because it's getting more positive, we can also call this end plate potential a depolarization. Okay, and we're going to see that depolarization is defined as really any time the inside of the membrane becomes more positive. Now, as this acetylcholine continues to come across this synapse, as long as you continue to have these action potentials coming down the neuron, then you continue to see acetylcholine binding. You continue to see sodium coming in. And what happens effectively is that this charge gets bigger, our depolarization grows until we hit threshold. At that point, you get that action potential that is now going to be generated down the length of the muscle cell. So we now go from this local end plate potential to a action potential in this muscle cell that's going to be propagating. So this is a lot of what we've seen already, but I'm layering in this idea of an end plate potential being a type of graded potential. And I'm also presenting this idea of depolarization. So again, if 0 is up here, right, as we move in really the positive direction, we are going closer to threshold. And as we go closer to threshold, we stand a higher likelihood of that particular cell being able to generate our action potential. Okay, so now let's take that to the nervous system, where we, or rather from neuron to neuron communication. So I've got a scene set up here where we have what I'm going to call our primary neuron here in red, and all of these other neurons that are going to be communicating with, right, so neuron here, 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 who are going to be sending signals to this neuron. So this is the axon of the neuron. This is the axon terminal. I've tried to draw some neurotransmitters hanging out at the base there. Now, the only way that those neurotransmitters are going to be released, i.e., the only way that this neuron is going to communicate, is if it passes those neurotransmitters on. And it's only going to do that if it's able to generate an action potential down its axon. So with the muscle cell, we saw that we had to hit threshold, and it's going to be the same case here. Another part of the axon that I want to highlight is this region here. We're going to call this the Axon Hillock. I also think of it as the trigger point, or the trigger zone, and I think that's going to become increasingly clear here in a second, or I hope that it does. So here we go. In contrast to a neuromuscular junction, right, we saw that this was only excitatory in nature. Our only option was to depolarize, right, to go in the positive direction to increase this. There was never a scenario where we would have acetylcholine coming across and that you would get a positive influx of, or excuse me, an influx of negative ions, or where you have more positive ions leaving. It always led to an increased positive charge on the inside of this cell. Okay, so again, with the neuromuscular junction, we always saw that the effects were excitatory. Okay, and in the case of the nervous system, they can be excitatory or inhibitory. Rather, events at these neurons can either be excitatory or inhibitory. So I want to continue on with this idea of a graded potential, and I hope that this graphic does a decent job of explaining this. So let's take one of these green neurons as an example. Let's say that hanging out at the base of this neuron is dopamine. Okay, so I'll just abbreviate dopamine for short. So in order for dopamine to be released and to act on this cell, right, we have to see an action potential going down this cell, right? So let's say that this neuron fires its action potential. You have dopamine coming across this synapse, and just as before, it would bind to ligand-gated receptors on the other side, on the post-synaptic side, that in this case happen to be along the dendrite of this neuron. So dopamine comes, it binds to these ligand-gated channels, and just as we saw with the muscle cell, it causes them to open. And in the case of dopamine, you again are going to have an influx of a positive ion. And as that positive ion, depending on how long dopamine is available in this space, in the synapse, and how long or how much of it is available to bind to these receptors, is going to determine how big of a graded potential we create. So as this dopamine comes across, you have a positive ion. I'm being generic and just calling it an ion at this point, that positive ion, and that positive charge is going to spread, and it's going to start to travel towards the axon hillock. So I'm trying to show some plus signs, right? Now let's say there's just a little bit of dopamine that is released here. What would happen is this positive wave would begin to travel, but it wouldn't get very far. So maybe it just gets that far. I erased some of my dendrite here, bring that back, there we go. So that positive wave would only travel so far. If this axon fired more action potentials, right? So down the length of the axon, then you would get more dopamine. And if there's more dopamine, that would in turn translate to a bigger wave of positive charge passing through this neuron. Okay, now the hope is that this positive charge would be able to travel to the axon hillock. So I'm going to pause there. And what we're really seeing here is that this positive charge, first of all, it's a graded potential. But what's happening here, zoom in on this a bit, is it is creating an excitatory post-synaptic potential. Okay, so let me grab a different color here. So what I'm saying is that in this space, so this is our synapse, right? This space is our synapse. And as this neurotransmitter passes across this gap, it is acting post-synaptically. And because you're getting a positive charge being generated here, it's going to be excitatory in nature. So we have an excitatory post-synaptic potential. It's a graded potential, it's excitatory in nature, and what we're really interested in is what is going on the other side of the synapse. So let me try to explain that again with another cell down here. So let's take this blue one down here. So same scenario, an action potential fires, neurotransmitter is released, so it comes across the synapse. And what we're really interested in here is what happens post-synaptically. So again, if this is our synapse, this is our gap, right? So this is our synapse, this gap between one neuron presynaptic terminal and postsynaptic terminal, right? We're interested in how we are affecting ultimately the membrane of this big red cell here, right? So assuming that this, whatever neurotransmitter is being released, assuming that it allows for the influx of positive ions to come in, if that's the case, then we will again see an excitatory postsynaptic potential. Okay, now let's travel over to this neuron over here. Okay, now let's say that in its terminal, we have a neurotransmitter. GABA is really the only inhibitory neurotransmitter that I'm concerned about you all knowing right now. So let's run with that. So again, GABA is a type of neurotransmitter, and it's going to be inhibitory in nature. So when this neuron fires an action potential down its axon, you have GABA released. And what GABA will do, rather than causing an influx of positive charge, is it will cause the influx of a negatively charged ion. And so let's take this scenario. I'm going to create a little bit more space here. But let's take the scenario where we are measuring along the membrane. And we have a probe, going to be a long probe. But here's our meter. It's a bit smaller, don't need to go crazy here. All right, so here's our meter. And it's a neuron, so at rest, we would actually see it sitting at about negative 70 millivolts, okay? So that's before this cell here fires, okay? So here's a graphic of our cell. Here it is sitting at negative 70 milliseconds over here, millivolts on the x-axis, and threshold is up here. So our neuron in red is happily hanging out at rest at negative 70. When GABA is released and you have the influx now of a negative ion, or rather this membrane becomes more negative, rather than going towards threshold, it starts to tuck away from threshold. And so this idea, rather than it being a depolarization as we saw before, this is going to be what we call a hyperpolarization. Sorry, I got a little messy there, but it's a hyperpolarization. So the inside of the cell membrane in this area is becoming more negative. And essentially, it's reducing the probability of this red cell firing an action potential. It's taking it further away from our threshold up here. And if it's further away from threshold, that means it's less likely to fire. Hyperpolarization. Okay, the cell grows more negative. Okay, with a depolarization, the cell grows more positive. So it comes closer to threshold. And so I want to link these terms with an EPSP and what we're going to call a IPSP. So an inhibitory, I should use purple, an inhibitory post-synaptic potential is a hyperpolarization, right? Because the cell is growing more negative, it is less likely to generate an action potential, and as such, it is inhibitory. So I'm trying to just link some of those vocabulary for you guys. In contrast, an excitatory post-synaptic potential is going to, in this case, we're going to see a depolarization, right? We are exciting the membrane because it's more positive, because it's now closer to threshold. So trying to just, again, and this is excitatory. So hopefully writing those terms out in that way may help a little bit with that. Let's go back to our scenario here. So our hyperpolarization, so we're becoming increasingly negative. Now the question is, what's going to happen with this scenario? So I've introduced this idea of an excitatory post-potential and an inhibitory post-synaptic potential. GABA is creating in this space, let's get a different color going for you guys here. Let's go with orange. So what I'm saying is along this membrane, so this is the synapse in this case. So this is presynaptic terminal. This is postsynaptic terminal. So in this space here, because GABA is creating a more negative charge, because it is creating a hyperpolarization, we can say that rather than it being an excitatory post-potential, as we saw up here, this is going to be, again, an inhibitory post-synaptic potential. Okay, so I'll give you a second to digest those, maybe pause the video. Now what I want to look at is the fact that graded potentials, so an EPSP and an IPSP, right? These are not action potentials. These are, again, graded potentials. And so a key feature of a graded potential is that these waves of energy, they degenerate, right? If you don't get enough neurotransmitter coming from these different cells, then they will just peter off. So this negative charge or the positive charge coming from over here, or the positive charge that I had drawn earlier coming from this cell, they'll just fade. So they're waves and they can lose their energy, if you will. Okay, and that's going to be in direct contrast to an action potential, which does not dissipate. Okay, so because graded potentials can either be inhibitory or excitatory in nature, that leaves us with a lot of different capabilities in terms of acting upon our red cell here. So I'm going to give us a clean slate, and I want to draw a few scenarios here where we are essentially going to add with these graded potentials. Okay, so we looked at temporal summation and spatial summation with the muscle cells, right? With temporal summation, that was a change in the frequency of action potentials firing, and that could lead to more force generated in the muscle. With spatial summation, we saw that you could have multiple motor units firing. Okay, so recall those ideas, and we're going to apply those terms to this scenario here. So let's run with, let's say this cell here, down here at the bottom, is now firing an action potential. And let's say that at its base, we now have GABA. Recall that GABA is going to be inhibitory in nature, and so a negative charge is going to start to spread. And notice I'm moving towards what I referred to as the Axon Hillock earlier, right? What we can also refer to as like a trigger zone here. Okay, so that negative wave is going to start to travel there. Let's say that at the same time, this green cell down here fires an action potential. Okay, when its neurotransmitter is released, it comes across, and when it binds, it allows for positive ions to come through. Okay, so a positive charge, this graded charge, is now going to start to travel towards this Axon Hillock. So you have a positive charge traveling and a negative charge traveling. Well, what can happen is they can essentially cancel each other out. So if the positive charge and the negative charge cancel each other out, then that would be essentially saying that we have a inhibitory post-synaptic potential coming from the GABA, and we are adding with it an excitatory post-synaptic, sorry, I'll clean that up a bit, excitatory post-synaptic potential. So we're taking those two, and basically they cancel each other out. And so you don't get enough energy, you don't get enough change in the membrane by the time you reach this hillock to generate an action potential down this red cell. Okay, so let me delete that scenario. Okay, now let's say we have a scenario, so clean this up a bit, where we have the two green cells firing. So here's our action potential. Neurotransmitter is released in the synapse. It binds postsynaptically, and this neurotransmitter is going to be excitatory in nature. And so because it's excitatory in nature, we are going to generate a positive charge. So this is an excitatory postsynaptic potential, and it's going to start to travel. And let's say maybe the cell only fires one action potential. So this positive charge would dissipate as it starts to travel, okay? And maybe it fades there and doesn't quite make it to the axon hillock. Meanwhile, this cell over here fires an action potential. Neurotransmitter is released, it binds, and let's run with this idea of it being the same excitatory neurotransmitter, which will create a positive charge. Now, think to yourself, is that a depolarization or a hyperpolarization? And hopefully you arrived at a depolarization, right? So we're exciting the membrane of this red cell. Well, what can happen is the positive charge from this cell down here can actually add with the positive charge from this cell here. And so what we can see is when they combine, if it's enough for the cell in red to hit its threshold, so what we've basically done, all right, here's our friendly milliseconds, millivolts, here's negative 90, right? And I'm going to draw in red, right? So our cell in red here is hanging out negative 90, and you get these two graded potentials that are basically adding. And if it's enough for it to reach threshold, then that red cell fires its action potential, which will travel down the length of the axon. Okay, so that's one way. And what I just illustrated is the concept of spatial summation in the nervous system. So again, spatial summation with the muscular system was when you took one motor unit, you fired it, and maybe it wasn't enough to move the load, and you needed more. So you would add another motor unit in a different space, and those two together would generate more energy or more force, right? And so in this scenario, what we saw is neuron 1 added with neuron 2, okay? And so that is this idea of spatial summation. That's also what I was illustrating over here when I had this cell, right? And we had a negative charge coming from the GABA. And even though they didn't add to be a depolarization that reached threshold, it was still addition. It was still this idea of spatial summation, right? Adding two different neurons in space. Okay, so that's spatial summation. Now I want to show you what temporal summation is. So clean this up. All right. Give us a little bit more space to work. Okay, so with temporal summation now, we are adding events in time. So we haven't really brought in this guy in the top left corner here. So let's say, I'll call him cell number 4. Let's say cell number 4 fires an action potential. And it fires one action potential, and it releases some of its neurotransmitter. And it binds to these ligand-gated channels on the other side. Let's run with the idea that it's an excitatory neurotransmitter that's being released. So we will generate an excitatory postsynaptic potential here, an EPSP, and so a positive charge will start to spread. But it only shot one action potential, right? And so with a graded potential, like I said, they degenerate, they fade. And so let's imagine that there's not quite enough of a positive wave, of a positive energy for this to reach the axon hillock, right? That doesn't happen. It just doesn't make it there, right? So we don't get that far. So in contrast, what we're going to see is that this cell can fire multiple times now. So it now fires one action potential and a second action potential and a third action potential and a fourth. And what happens is they add in time, and it can be enough that you now get a bigger wave of positive energy traveling towards the hillock, and it takes our cell in red from this rest. The positive charge adds, another action potential fires, right? And you hit threshold because of all of those firings, and you get your action potential that's now going to spread down this cell. So that is temporal summation.